This is Professor Clark, and in this video we're going to do an example from Chapter 5. In Chapter 5 we are comparing two proportions. So here's a problem from the book. It's a study of tamoxifen and relaxafene. So researchers reported the following findings from this study of tamoxifen and relaxafene, a study involving postmenopausal women who are at an increased risk for invasive breast cancer. In the study, 9,726 women randomly assigned to use tamoxifen daily. 163 developed invasive breast cancer. And of the 9,745 who were assigned to use relaxafene, 168 developed the breast cancer. So I think the question is one of these drugs better than the other at preventing invasive breast cancer or something like that? Or maybe does one cause it more than the other? And so it looks like we've got two groups, a group of women taking one drug and a group of women taking another drug, and then we've got a proportion who developed the breast cancer and not, and then we've got a bunch of questions. So number A, is it an experiment or an observational study? Explain what you're deciding. Identify the explanatory and response variables, identify whether it's categorical or quantitative, organize the data into a 2x2 table, and then find the observed difference in proportion for the breast cancer cases between tamoxifen and relaxafene users. So let's take these first four questions first. So in this case, so I've put the answers here, but in this case we've got a randomized experiment. We had two groups of women. They, used some sort of randomization process to assign one treatment or one drug to one group and the other one to the other group. So we've got an experiment. What's the explanatory variable? Well, we've got two variables in play. One is whether they got breast cancer or not, and one is what drug they took. And in this case, the explanatory variable is what drug the women took, either the tamoxifen or the relaxafene. And that's a categorical variable, right? It's this or that, it's yes, no, that kind of thing. It's not a number. And the response variable is whether they developed the invasive breast cancer in the next 5 years. That's also a categorical variable. That's yes or no. And here's the data. So we took these numbers from the study, right? And then we just put it into a table. So there were 9,726 who took tamoxifen, 163 developed the breast cancer, and you can subtract these two numbers to find the number that didn't, right? They don't give you that number, but you can subtract it. And then the relaxafene, 9,745 got that drug, 168 developed the cancer, and then you can subtract them to get that. So that's how these numbers come from, and that's how these numbers come from. And then the totals, well, you can just add this up. So how many women got breast cancer, how many women didn't, and how many women were in the study. So you can just add these two to get there and there. So that's a two-way table. And then the question is the proportion of women who got breast cancer in this column different from this column, right? So what's 163 over 9,726? Well, that's this number. If you punch it into your calculator, it's 0.0168. So it's pretty rare, but not, it does happen in a little over 1% of the time. And in the other group, it's 168 divided by 9745, so 0.0172. And you can see these two proportions are very similar to each other. The statistic that we want to look at is the difference in the proportions. So in this case, if we take this one, 0.0168, minus this one, 0.0172, we get negative 0.00048, which is fairly small. But it's not zero. So it is possible that the incidence rates for these two groups are different, maybe only different by a very small bit, but different nonetheless. And that's what the statistics will tell us. So the second half of the question says, okay, let's set up a statistical test. So what's your null and alternative hypothesis? Is it okay to use a theory-based test to find the p-value? Okay, do that then. Do the study. Use an applet, get the standardized statistic, get the theory-based p-value, and then state a complete conclusion about significance and estimation, causation, generalization, and explain how you're arriving at your conclusion, right? So this is sort of the second half where we're actually doing the statistics. So let's do that. So let's take a look at the answers here. So the null hypothesis is that the true long-run proportion of postmenopausal women who take tamoxifen and develop breast cancer, pi t. Okay, so that's pi. That's a true proportion, right? This is a parameter, whereas these numbers are our p hats, right? Those are statistics. That's the proportion from the sample. But what our null hypothesis is about is the true proportion in the population. Is that the same as the true long run proportion of women who take relaxafine and develop breast cancer, pi r? So the null hypothesis is that pi t is equal to pi r. The alternative is that they're different. And so we could write this out in symbols. The null hypothesis is that pi t minus pi r is 0. If they're the same, then the difference is 0. And the alternative is that pi t minus pi r is not equal to 0. So we'll give it the benefit of the doubt, and then if we have evidence, we can conclude that they're different. Now, because this study was comparing two proportions, to use a theory-based test, we need to have at least 10 successes and 10 failures for each variable. That is, we need at least 10 in each of the 4 entries in the two-way table. Let's take a look. 10, 10, 10, 10. Yes, all these numbers are bigger than 10, much bigger than 10, so there's no issues here. Which is satisfied by the data. So in other words, the sample is large enough for the null distribution to be approximately normal. That's what it means to use a theory-based test, is to say, well, if we made the null distribution by a simulation, we're going to get a normal distribution anyway, so why not just cut to the chase and do a normal distribution? So that's question F. Why is it okay to use a theory-based test? And then number G says, okay, well, let's get to the applet and do it. All right. So you can see the numbers are going to come out. Let's switch over to the applet. Okay, so first, what applet are we going to be using here? Well, we've got two proportions, so let's use the two proportion applet. If you click on that, it'll bring up an applet that looks like this, but of course these numbers aren't correct. So what you're going to do is enter those numbers in. Okay, I already did it for you. And then if you click Use Table, it will make this bar graph here, and you can see, well, very few women, ended up getting it. It was only like 1%, right? So these, you can just kind of barely even see the difference here. If you scroll down, you can see the observed difference. Well, it's only giving us 3 decimal points here. Remember, when we computed it, we got negative 0.0048, but it's not quite showing us that there. And then to do a simulation, well, you would just click, 1,000 and, click shuffle, and it should make a null distribution for us. Now, because these numbers are so big, this one will actually take a little bit of time to do. We could have also used a theory-based applet, right? We could go here to theory-based inference, and when you do a theory-based inference, you want to be a little bit careful, because when you enter the numbers in, it looks a little bit different than when you enter it here. So for theory-based, you'd have to go, well, not one proportion, we've got 2 proportions, right? And in this case, you enter the total here and then the number that got the breast cancer here. So it's a little bit different than this one, where you enter sort of the successes and failures and it makes the totals for you. In the theory-based, it kind of goes the other way. So the total was 97.26 for one group and 97.45 for the other group, and then 163 developed breast cancer in the tamoxifen group and 168 developed breast cancer in the other group. It computes the proportions for you, and if you calculate, it'll make those bar graphs. Again, it'll subtract the 2 for you, and then to do a test, you can just go over here. It was a 2-sided test, and if we hit calculate, it'll give us the p-value, 0.7954, and the standardized statistic, negative 0.26. And what that means is our observed difference, which was negative 0.00048, that's right about here, that is 2.26 standard deviations to the left of the mean of the null distribution. And if we go over here to this one, we should get exactly the same kind of thing, right, in the simulation. The p-value is 0.772, which is pretty similar to our theory-based p-value, which was 0.7954, right? They're not going to be exactly the same, but they're going to be close, and it gives you the theory-based p-value down there. if you click that little button. And you have to type the number in, right? And click beyond because we want two-sided. So that's how you do the simulation. That's how you do the theory-based. And then I think it asks for the confidence interval as well. So if you just click the confidence interval button, it'll give you the confidence interval for 95% confidence interval right there. Okay, so that's the statistics happening. Let's go back to the answers and actually write it up. So there's our p-value and our standardized statistic. Of course, the simulation is going to vary from time to time what exactly number you get, but the theory base should hold pretty steady. Okay, so what conclusions do we make? Well, our p-value is really large, right? The observed statistic was right in the middle of the null distribution. Our difference was almost zero, right? So it was just right smack dab in the middle. So that didn't give us evidence that these things were any different, right? So because our p-value was very large, 0.79, we do not have evidence that the true long-run proportions of women who develop breast cancer is different for those who take tamoxifen versus relaxafene. So it's possible that they're different, but we don't have any evidence that they are, right? That's what you want to say. We do not have evidence that those true long-run proportions are different. We can do a confidence interval, so our theory-based confidence interval was that, which means that we're 95% confident that the true difference between the parameters pi t minus pi r is between negative 0.0041 and 0.0032. Since 0 lies in the interval, it's plausible that the two proportions are equal. They may very well be different. If they are different, it's probably somewhere in this interval, and you'll notice the interval's pretty close to 0. If they are different, it's only by a little tiny bit, right? So it's not a very big effect even if they were different, but we don't have any evidence that they are different. Causation. So this was a randomized experiment. So if we had found an association, we didn't, we could have concluded it was caused by the different treatments and not something else. And then generalization, the study involved postmenopausal women at risk for this cancer, so we would only generalize to that population. It didn't tell us if it was a random sample. If it were a random sample, that would give us the ability to generalize. So we're not exactly sure how representative the sample was, so I've got, this would be at best maybe what you could do. They didn't really tell us, was the sample from the United States, was it mixed races, mixed ethnic groups, mixed, socioeconomic statuses. If you really want to talk about generalization, you should know more about the sample. So we'll just kind of carefully say, it probably could be generalized to other postmenopausal women, but I've got some questions. And that's how you would do a problem like this from stem to stern. Thanks for listening.